Hello.
Good morning. Hello. Good morning, everybody. We'll get started in about 5 minutes.
Josh. There. What are you gonna leave your day for? Huh? You're gonna buy theirs?
Hey, can you wait a second? I need to get something.
Sure.
Yeah. Still people here with my teacher. You like don't have. We see the oh, here. Oh, that's on okay, Mom. Long day. Josh, get away.
We'll get started here in a couple minutes.
No. Two people and the teacher and me. There's only the teacher and two other people.
Okay, we're going to go ahead and get started. Other people might join later. Let's see. I need to share my screen with you, but I kind of wanted to go over, well, let me just go ahead. Oh, some more people coming in. So let me go ahead and share my screen with you. Okay, so what we're doing today is, we're still looking at Newton's third law, which is what you guys were learning last Wednesday. And we're just gonna kind of review it and kind of do a short lab I found online, which is kind of nice. I didn't think I'd find anything. That's probably all we're gonna do today. And then on Wednesday, we'll kind of review Newton's third law again. That'll probably be the last time that we review it. And really what we're gonna be doing is reviewing all the way up until the final of all the stuff we've done this semester, which really has only been 2 units, and that has been looking at motion. That's where you had to draw motion maps with the dots and the arrows and velocity and acceleration, and then this unit dealing with forces. Okay, so let me click on the agenda. So the first thing we're going to do is we're going to watch a couple of videos. And then after that, I'm going to kind of show you the lab that you're going to do. And then you're just going to work on the lab on your own. It shouldn't take that long, I don't think, especially after I show you. And then after you've done the lab, then you're going to take your answers you get from the lab and you're going to use those in the quiz, the attendance quiz. So the attendance quiz is just making sure that you've done the lab. It'll also let you know whether you did the lab right or not, because if your answers are wrong, then that means you didn't do the lab right. Okay, so I'm hoping that I can show these videos. So let me stop for a second here. 1 second. All right, let me move this out of the way. I know you can't hear that, but I need to see if I can get this set up right. So let me stop sharing first. And then I think there might be a way I can just share computers. Okay, so can you unmute yourself for a second? Because I'm going to try, I think I could share the video and the sound with you. So if you can't hear the sound, I would like you to say, hey, I can't hear it. That way I can stop and I can figure out something else. Okay, so here I'm getting ready to share it. Okay. So let me go ahead and start the video. This thing's always in my spot. Okay. Let's see. Sorry, it's hard. Here we go.
Description.
Okay.
If you ever want to.
Sorry. Can you guys hear the music? You can hear it? Okay. All right, cool.
This is a water jetpack, but no, that's not me flying it. This is me. It's harder than it looks, okay? But to understand how it works, we need to first talk rocket science. Rocket science is meant to be one of the most complicated things in the world, but the basic principle is incredibly simple. It's just Newton's third law. All forces come in pairs, which are equal and opposite. To demonstrate this, I'm using a fire extinguisher on a skateboard. As the carbon dioxide is forced out the back of the extinguisher, it puts a force forwards on me, causing me to accelerate. Or that's the theory anyway. If you look closely, you can spot the exact moment I realized this is a fail. So what was the problem here? Well, the force applied to me by the carbon dioxide is equal to the rate of mass ejected out the back of the fire extinguisher, call it m dot for short, multiplied by the velocity of that exhaust gas. So in this case, the carbon dioxide wasn't ejected fast enough to create a big enough force and overcome the small frictional forces to get me to accelerate. But it can be done, as has been demonstrated many times on YouTube. When the space shuttle lifts off, exhaust gases exit the nozzle at 3 to 4 kilometers per second, ejecting an amount of mass of 9,000 kilograms per second. This creates thrust equal to 30 million newtons, or the equivalent of about 2 million decent fire extinguishers. Now, imagine you're an astronaut preparing for launch in the space shuttle. You would be seated not vertically, but horizontally, perpendicular to the acceleration. And that's because the human body is a little bit like a water balloon, where the water represents your blood and the balloon represents your harder parts, like your skeleton. Now, if you're accelerated up really quickly, then your skeleton accelerates up at that rate, but your blood tends to stay where it is. And this results in the blood ending up in your feet. Now, since there's not enough oxygen going to your brain, you would black out. But fighter pilots face an arguably worse fate when they accelerate down too fast, because then the blood all rushes to their head and they suffer something called a readout, where the blood actually comes out of their eyes, nose, mouth, and ears. But back to astronauts. Since you're reclined, at worst the blood will end up in the back of your body and the back of your head, but your brain will still have enough oxygen to remain conscious. Now, as the spacecraft lifts off and starts speeding up, the acceleration is initially a very reasonable 5 to 8 meters per second squared. That's less acceleration than an object in free fall here at the surface of Earth. But as the spacecraft continues to burn fuel, its mass decreases while the thrust remains essentially constant. Newton's second law says that the acceleration of an object equals the net force applied to it divided by its mass. So as the mass decreases, the acceleration increases. And it increases at an increasing rate. So much so that at the end of the rocket burn, the thrust has to actually be limited in order to keep the acceleration from going over 3 Gs. That's 3 times the acceleration due to gravity, or about 30 meters per second squared. Now, the term G-force has been invented to give a sense of the amount of force experienced by astronauts in multiples of the force we experience every day. Right now, you're experiencing 1 G-force, probably on your butt if you're sitting down. Can you feel that force? But accelerating at 3 Gs, you would experience 3 G-forces. So the force between your back and the chair would be the same as if you had 2 of you stacked on top of you. Oh. Oh,
hey, pipe down below, huh?
Oh, you guys are heavy. Oh, man. You know that feeling when you're taking off in a plane and it feels like you're pressed into the seat? Well, really, it's the seat pressing into you. But if you imagine that feeling times 20, that's what it would be like to be taking off in the space shuttle. Now, an interesting little side note is that we think of the space shuttle's acceleration as being mainly vertical because that's what we see when it lifts off. But that's actually not true. Once the space shuttle exits the thicker part of the atmosphere, it turns horizontal and accelerates up to its orbital velocity of 28,000 kilometers per hour. So most of the acceleration of a spacecraft, in orbit anyway, is horizontal. So how is this like a jetpack? Well, unlike the shuttle, you don't carry your own propellant with you. And also, there's no chemical reaction releasing energy that drives the propellant downwards. Instead, the jet ski pumps water out of the lake and up that hose at a rate up to 60 liters per second.
And then right on these nozzles here, the water changes direction, so it goes from coming up to being fired out the bottom. And that change in momentum as it goes over the bend is what actually pushes the jetpack up, because the jetpack's pushing down on the water. So by Newton's third law, the water has to push up on the jetpack,
generating 1,800 newtons of thrust. That's roughly equivalent to 150 decent fire extinguishers. This could accelerate me at up to 1.5 Gs. And you use your hands in order to steer, lifting up to drive yourself upwards, moving your hands down to accelerate forwards, and pretend like you're turning a big wheel very gently in order to turn side to side. One thing you don't want to do is try to explain the physics of the jetpack while in the air. That's what I was trying to do here. While you're learning, your thrust is controlled by your instructor. So if he sees you doing something stupid, he'll just turn off the thrust and drop you into the lake so you don't hurt yourself. That's generally a good idea unless you're on a collision course with the jet ski. I got a pretty fat lip from doing this, but luckily all my teeth were intact. When the thrust is equal to my weight plus the weight of water in the hose, then I can hover or move with constant velocity. It's a common misconception that you need a little bit of unbalanced force to move with a constant velocity. In truth, if the forces are balanced, you will just continue moving with whatever constant velocity you have. The other common misconception about rockets is that you need something to push off like the atmosphere. In reality, what you're pushing off is the propellant. So even without the air around, a water jetpack would still work because you're pushing off the water that is coming out of those nozzles. If you want to go jetpacking, I recommend you go easy on the controls. I mean, the worst thing you can do is overcompensate, which I think is a typical human reaction. Because you're reacting to where you are and how fast you're moving, and you're not reacting to acceleration, which is the real thing that you can control. So even if you're coming down towards the water quite quickly, you may be slowing down, so it may be okay, and you don't need to adjust anything. You just kind of need to trust that the jetpack will get you out of any trouble.
It's a pretty incredible experience. Feeling the power of that water rushing past you. It's the closest I've gotten to flying, really. Yeah. It's the power of physics.
Now, many of you may not know that I have a second channel called
Okay, so I thought I'd share that video because what you found last week was that the forces, first of all, occur in pairs. We call those interaction pairs. And those forces are the exact same size, but they act on different objects. So in this case, you saw that there was a force on Derek, that was the name of the guy talking, and it kind of pushed him up in the air. But there was also a force on the water that was being shot out, and that's why that water was being shot out. And it was in the opposite direction. And so I think that kind of helped you kind of see what was going on there. Earlier on in the year, we learned about drawing system schemas, and then of course, then we started drawing force diagrams. So I want to watch another short video that shows how to incorporate system schemas to figure out what the interaction force pairs are. So let me go ahead and share that video with you.
Yeah.
Actually, let me stop sharing. Sorry.
And free body diagrams for each of the objects involved in the situation. Our situation
First, can you guys hear?
Yeah.
Okay.
is going to be surface of the earth, a table with a cup of hot chocolate. So our objects in our system schema are going to be the cup, the table, and normally we would have included the earth and the ground as two different objects. Because the earth and the ground really are connected together, and it's going to make more sense when drawing a free body diagram of the earth and the ground to have them as one object, we're going to include them as one object on our system schema.
So she's drawing a system schema, which is kind of what we did at the very beginning of forces, and I'm going to go ahead and continue on. We also did this back with energy last semester too.
You can feel free to do that in the future. Whenever the ground or the surface is connected to the earth, you can include those as one object. So, to now draw our interactions. There is a gravitational interaction between the cup and the earth, and the table and the earth.
Okay, let me pause right there. If you remember what we did, now she only drew a line, but I asked you guys, if you remember, we were drawing double-headed arrows. And so each one of those lines with double-headed arrows on it, that's an interaction pair. So she said there's a gravitational force between the gravitational interaction between the cup and the earth, and there's a gravitational interaction between the earth and the table. So those are two different interaction pairs.
Now the table is resting on the ground, so the ground must be supporting the table with a normal force. And there is contact between the cup and the table, so that's two surfaces in contact that are pressed together, and that is another normal force.
Okay, and then now she just drew two more interaction pairs, and those were normal forces this time between the cup and the table, and the other interaction pairs between the table and the ground. Those are normal forces. Those are interaction pairs.
So this is all of the interactions. Now what I'm going to do is color code each interaction a different color. Now we're ready to draw a free body diagram for each of these objects. So the cup is going to be here, and the table, and the earth, ground combination. So I need a dot to represent each object.
So she's getting ready to draw a force diagram for the cup. So if you look at the picture up here in the upper left, you'll see that, oh, if you have to draw a force diagram, will it be balanced or unbalanced? Balanced, right. Yeah, exactly, balanced. And if you look at the cup here in her system schema, there's two forces on it. There is a normal force and a gravitational force. So she's getting ready to draw those in.
I'm going to start with the free body diagram for the cup, and what I'm going to do is when I draw one force, after I draw that force that's on the cup, I'm going to go ahead and draw the other force that's part of that interaction force pair. So I'm first going to draw the force of gravity on the cup, but then I'm going to draw the other force that's part of that interaction force pair, and I'm going to draw the force of gravity of the cup pulling on the earth. So let's start with the force of gravity. So this is the force of the earth on the cup. That is a gravitational force. Now the other force that's part of that interaction force pair is a gravitational force of the cup pulling up on the earth.
Okay, so what she's going to do, instead of drawing the FN now, she'll draw it in a little bit, but she just drew one half of the interaction pair. She drew the force of gravity on the cup from the earth. If you remember the way we did it, we called it FG, and then we did C, comma E. So FGCE. That was because that's the feeler dealer. Now she's getting ready to draw the other side, the other arrow that's acting now on the earth and is coming from the cup.
Well, that's going to go on the diagram of the earth. It has equal length, equal magnitude. These forces are the same size, but opposite in direction. And then we will color code them. That is the pink force. And be sure to label it. So this is the force of the cup on the earth, and this is a gravitational force.
So over here on the left, this would have been FGCE. It's the force of gravity on the cup from the earth. But over here, this is the force of gravity on the earth from the cup. So it would be FGEC. We switched the subscripts. On the left, it's FGCE. So C is first, then E is last. Then over here on the right, it's force of gravity on the earth from the cup. So it's EC. We switched them. Notice how the direction is switched too. They're in opposite directions. The sizes are the same. That's why she made them both pink. What I want you to see is the one on the left works on the cup. It acts on the cup, and the one on the right acts on the earth ground. So those two forces do not cancel. That's one of the misconceptions that students usually have. They're like, oh, if it's an interaction pair, since they're equal and opposite, they cancel. No, they don't. And the reason they don't is because they act on two different things. The one on the left acts on the cup. The one on the right over here acts on the earth ground. Two different objects, so they don't cancel.
Usually, if you were to drop a cup, you would notice the cup accelerating towards the earth, but you would not notice the earth accelerating towards the cup. And that's just because the mass of the earth is so tremendously large that you don't notice the acceleration. It's not measurable. It's just so small. Now back to the free body diagram of the cup. We have drawn the force of the earth on the cup. There's one more force on the cup, and that is the force of the table on the cup. And that's an upward force. And because the forces on the cup are balanced, I know they're balanced because the cup is not accelerating up and down. This force has the same magnitude as this force. And that is the force of the table on the cup. And that is a normal force.
So we label that FNCT. It's the force of normal on the cup from the table.
And let's color code that. Now, where's the other force that's part of this interaction? Well, this force was the force of the table on the cup. The other part of that interaction is a force of the cup on the table. The cup is pushing down on the table.
So if you look at the picture, it's hard to see from the schema, but if you look at the picture, that cup is on top of the table, so it's definitely pushing down on the table.
And so the force, once again, interaction forces always have the same magnitude. So this has the same length as this. And that's color-coded green. And labeling it, that is the force of the cup on the table.
So the feeler dealer would be force of normal on the table from the cup, so FNTC. Whereas over here, it's FNCT. We reverse those orders. And that helps you remember that the direction's reversed. They don't cancel though, because they're on two different objects. The green force over here is on the cup, on the left, and in the middle, that green force, which is downward, is on the table. Interaction pairs do not cancel.
So now we finished the free body diagram for the cup because I can see there are two forces on the cup and I have both of those forces on the free body diagram. And you'll notice that the interaction force pairs do not show up on the same force diagram. The other pink force was over here and the other green force was over here. Okay, so let's do the free body diagram now for the table. We already have drawn the interaction between the cup and the table on the free body diagram. Let's draw the force of gravity. So I'm thinking about how long to make the arrow for the force of gravity. I'm going to make it longer than the force of gravity that was on the cup because I think the table would have more mass. I'm sure it would have more than twice the mass, but to make it fit well on the paper, here we go. So this is the force of the Earth on the table, and that is a gravitational force. And where is the other force that's part of this interaction force pair? Well, we've already drawn the force of gravity on the table, so there must be a force of gravity of the table on the Earth. The table's pulling upward on the Earth. So force of gravity. So we have force of the Earth, force of the table, on the Earth, and that is a gravitational force. So these are the two forces that are part of the interaction, gravitational interaction of the table and the Earth.
Again, notice they're on two different objects, so they don't cancel. They're same size, they're in opposite directions, but this one over here in the middle is on the table. This force over here of gravity is on the Earth.
And on the table, we have one more force. That's an interaction between the table and the ground. So it's a normal force. The ground is pushing upward on the table. So how much does the ground push upward on the table? Well, it has to balance the downward forces. So it's going to be equal in length to this one plus this one. So about that long. And that is the force of the ground on the table. Now where is the other force that's part of that interaction? This is the force of the ground on the table, so the other force is the force of the table on the ground. The table is pushing downward on the ground with an equal amount to the amount that the force was pushing up on the table. So this is the force of the table on the ground. And that is also a normal force. And these forces were blue. So that's an example of how to draw a color-coded system schema diagram where each interaction is a different color. And then on the free body diagrams, we can see where the different forces are that are part of each interaction force pair. And you notice.
Okay, so what I wanted you to see, this kind of pulls everything that we've gone together with forces, is that if you draw the system schema, you can actually see where all the interaction pairs are. So for instance, for the forces on the cup, there's a force of gravity on the cup from the earth, but then there's an interaction, the other half of the interaction pair is a force of gravity on the earth from the cup, and it's upward. Those two do not cancel because they're on two different objects. There's a force on the cup from the table, a normal force. Well, there's also a normal force on the table from the cup that's in the opposite direction. Those two don't cancel because they're on two different objects. And she went ahead and drew the other ones, so you can see that none of those interaction pairs cancel. And all the interaction pairs are actually these lines from your system schema. Okay, so let me stop sharing that then. All right, so now going to the lab then. So again, what we're looking at in Newton's third law is that forces always occur in pairs. They act in the opposite direction on two different things, and therefore they don't cancel. Sometimes they don't give you the same effect. In fact, let me go back to this picture here. Sometimes they don't give you the same effect. Like if you were to drop a cup, you would say, oh, that cup really is accelerating downward, so there must be more gravity on it than on the earth. No, it's the same amount of gravity. You can see the arrow was the same size. The reason we don't see the earth accelerate upward, we only see the coffee cup fall downward and accelerate, is because that cup has very little mass, very little inertia. It's not very lazy, and so therefore it moves really readily. But for the earth, there is a force on it, and it does accelerate upward a little bit, but it's so small that we can't really measure it. And that's because the earth is so massive. It has so much inertia. It's so lazy. It doesn't move perceptibly. We can't actually see it. Okay, so now we're going to look at the lab that I'm going to have you do. So let me kind of explain the lab. And again, I don't think it'll take very long. So I'm going to go ahead and open this up so you can see it. So the simulation we're going to go to here in a second is going to have a simulation kind of like this picture here. Let me explain what's going to happen. You see these two boxes here that have red question marks? When you go to the simulation, they won't be red. It'll just be white. And that's really the only thing you're going to be changing. You're going to put different force numbers in there. Those force numbers, I kind of give you a little hint down here, this note. The numbers you can put in there is going to be between -10 and +10. And it's not going to be like 3.2 or something like that. It's going to be like -10, -9, -8, or 7, 6, you know, something like that. Nice integer number. Same thing for this one over on the right hand side. You just have to play around with it so that it produces these three graphs here. In other words, they're going to move together. Okay, let's call all the direction to the right positive and everything to the left negative. Okay, then what you're going to do in the lab is just simply fill out these blanks. So for the observations, you're going to write down in your blank, maybe in a separate sheet of paper so you don't lose it, you're going to write down what force you put in this first red blank here, okay? So, and then for this other second red blank that actually worked, whatever force you put in, that's what you're going to put on this blank. So let me go ahead and open up the website so you can see what I'm talking about. Okay, now I'm going to go ahead and hit play. And do you see how they're not moving together? I'll hit pause here in a second. Hit pause. Okay, where's it at? Oh, let me go back and download it again. Sorry about that. I want you to look at the picture here again. Do you see how they move together in this picture? That's what you want it to do. You want them to move together. But if you look at my picture, they're not moving together. In fact, I'll keep going. You see the red one's moving, but the green was not moving. So evidently 0 and 0 don't work. That's not the right answer. So if you look at the graphs, look at those three graphs there. They do not match what the answer should be, okay? They have to match that exactly. So I'm going to hit rewind. Let's hit rewind. Oops, why is that? Oh, here we go, rewind. I can make these be whatever I want, okay? And you should be thinking about action, reaction, right? Interaction pairs. So let's say I'll have this be 5, and maybe I'll have this one over here be 7. Let's just see if that works. Oh, that's close, but no, that didn't quite work, did it? No, that didn't work. Okay, so let me hit pause. If you look at these 3 graphs, look at those 3 graphs, they did not exactly match this graph here. So you just have to keep on playing around here. So I could say, let's say negative 3. And this one here, I could say, I could say positive 3. Let's see what happens now. Oh, I'm getting closer. Still not right. Okay. Your hint again is action, reaction, interaction pairs. Okay. So I didn't quite get it there. If you look at the graphs, they don't quite match. So you just want to play around until you get to the match. Once you know what the numbers are, let's say my answer of -3 and +3 are right. Then what you're going to do is on this blank right here, you're going to put in that first answer. And I said it was -3, which is not, but let's say it's -3. And on the second blank, I'm going to put my second, whatever that one was, +3. Of course, that's not the right answer. And then you're going to go ahead and do the applications. So for instance, if you look at this first application, it says 12 plus this blank. Well, this blank right here, it says PRG is the same as this one. Whatever you put there, you're going to put here. And you just simply take 12 plus whatever that number is, and it gives you this answer. And then to find the acceleration, you're going to take that net force that you just found, that's net force, and you're going to divide by the mass. So right here it says you're going to take the net force divided by the mass. And it tells you right up here in the note what the masses are. The mass of the red block, which is bigger, is 2, and the mass of the green block is 1. So you're going to take your net force, whatever that was, and in this case, you're going to divide by 2 to figure out what your acceleration is. And then you're going to take your net force of the green one. Well, if you look right below, it says PGR. So whatever you have on this blank here, it's the same as this one. And to find this last answer, you're going to take that net force that you found, the net force, whatever this blank is, and you're going to divide by the mass. And again, the mass of the green one is 1 kilogram. And that'll give you the acceleration. Okay, so that's going to be your homework. And then one more thing, let me go ahead and show you. As soon as you get those answers, then you can go ahead and do this attendance quiz. And there is a code, so I need to give you the code. So maybe write down this code on a piece of paper.
Can you slow down during this part, please?
I'm almost done. I'm almost done. The code is, the code is 45, lowercase q, lowercase w, 78, E, and $. 45, QW, 78, E, $.
E, the $, the
Again, it's 45, QW, 78, E, $. Okay, when you go into the quiz, there's only 6 questions, and the 6 questions are, let me quickly go over that. The 6 questions are these blanks on the far right. So this blank here, this blank here, this blank, the acceleration, this blank, and this blank, okay? That way you'll know right as soon as you plug them in if you got the right answer or not. So if, for instance, you missed some, then that means, oh, I need to go back and do that quiz again. I must have did something wrong probably, okay? So that's kind of it. Let me go back and give you the code one last time. It's 45QW78E $. And down here for number 5, you don't have to get started on this if you don't want to for number 5. It's not due for homework or anything because we're going to whiteboard that on Wednesday. But I've already shared these folders with you in Google Drive. With each student, it's the next worksheet we're going to do. So if you want to get started on that, you can. So then on Wednesday, we're going to have a meeting where we're going to whiteboard that worksheet. Does anybody have any questions?
Nope.
Okay, let me stop sharing, and I need to get your smiley faces for attendance. I hope you're all doing well. This is weird. I hope that we don't have this next fall. I miss you guys. Okay. So everybody doing all right? I miss you guys.
Feel right.
Okay.
Yep.
All right. Well, I guess I'll see you later. It's good seeing you, everybody, this morning. All right, bye.
Yep.
See ya.
Bye.
Noah, you okay? Okay. Mr. Alger, how you doing?
Good, how are you?
Good, good. So I hope they're going to do all right. It's the school's already, I don't know if you've heard the rumors, the school's already thinking about next fall, and they're going to start talking about what the schedule might look like next fall. It's just in case kind of a
Yeah.
scenario, but it's kind of scary. So
Is it like limited attendance and
yeah, I think what they're talking about is kind of like kind of a rotation, like 25% of the students on any given day, like maybe Monday, 25%, and then, Tuesday, the next 25% and so on. And then Friday, just as an office hours kind of a day. I kind of like the idea because, there's some students that, like, for instance, didn't come today and they just kind of fall off, the face of the world as far as I know. I think it might be a good idea to get them in class. Maybe I started thinking about this. I almost think maybe they ought to just come every day. I don't know.
yeah. No, that would be nice. Be
Yeah,
able to focus in on them a lot more too.
Because
Did he sorry.
That's
Did
right.
he Mr. Ginner talk about that in that video or whatever?
I'm not sure if he did or not. He asked me on Wednesday when was it? Last Friday. He asked me if I'd be willing to kind of sit on a committee. He's going to get together next Friday to kind of talk about, just brainstorming what it would look like.
Oh, okay.
So I've already been thinking about it. My other classes, I'm okay with just every 25. I think they're going to do it by alphabet. That way,
Yeah.
all the kids from one family can be there the same day, so it's easier for parents, I think, which makes a lot of sense.
Yeah.
But I started thinking about, especially my physics first kids, there are some students that I think it'd be better if they came every day. So
Yeah.
I don't know.
Be like an optional kind of thing too.
Yeah, I mean, well, you know who some of them are. They're just not showing up. I mean, there's some students that are doing phenomenal now.
Yeah.
So it works for them, but it's definitely not working for everybody.
That'll be wild.
Yeah.
It'll be really weird.
I was just wondering have you heard anything about, because I think there really ought to be some people from special ed that can come in and kind of.
Yeah, get some input in. No, I haven't heard anything. We had a couple meetings last week, and nothing was said. I got another one. I think it's tomorrow. So maybe they'll say something about that then. I'm not sure.
Yeah,
I'm sure some other people have heard the rumors, so they'll probably bring it up.
Yeah, I mean I just want to make sure that's on the radar, because I think it works. This thing that we're doing kind of works for a lot of the students, but it doesn't work for every one of them.
No, I agree. Yeah.
All right. Well, I think that's it for today. So I think it went okay. They seem to
Yeah,
be.
yeah.
Yeah.
Let me know if anybody needs help or anything, and
I will. Yep.
emails too. So
Yep. All right. Okay.
All right.
See you. I guess tomorrow. You're going to come
yeah,
tomorrow.
nice.
I'll send the email. I forgot to give you the code, so I'll go ahead and do that.
Okay.
All right.
All right.
See ya.
See ya.
Corey, did you have any questions? Okay.